Hi guys, good morning. Hope everybody is ready. Shall we start? You're not ready, guys?
We are ready, sir.
We are ready, sir.
Yes. Okay, cool. So last class we solved problems on Nernst equation. I think everybody is familiar with it, how to approach the problems. So whatever kind of problems will be given to you with respect to Nernst equation, I think you'll be able to solve, right? Okay, right. So today we are going to see thermodynamics of electrochemistry. Nothing, it's like only the name is very big. It's just one small equation which you're going to work with, and I already know what is the equation, right? So I'll be able to connect my reduction potential value with my delta G, and we already know what is the equation, isn't it? So my delta G is equal to minus NFE. So this is the equation which I'm going to connect. Okay, fine. What we're going to do here is basically say if I have A giving products, or say whatever A giving products is one reaction. Okay, and say for this reaction I have E or E1 as the reduction potential. Okay, now when I reverse the reaction, say when I write products giving A, that is when I write the opposite backward reaction of this, now I will be able to easily write it as minus E1. This I'll be able to do. Okay, but say if I have A giving B, B giving C, and say this is E1 and this is E2, right? And if I go for and I want to find the reaction, I want to find the reduction potential value for A giving C, right? I have given you A giving B, the reduction potential, the potential of the reaction is E1, and for B giving C it is E2, and I ask you to find A giving C, what will be the potential value. Now what will you do generally? Now when I add these two reactions, when I add A giving B and B giving C, I'll get A giving C, correct? Now in this case, can you write it as E1 plus E2? Absolutely not. It is not an intensive property. Okay, so I hope you understand what is an intensive and extensive property in thermodynamics. Intensive properties are going to depend upon the amount. Sorry, they are independent of the amount, and the extensive properties are independent of the dependent on the amount. Anyways, so what you have to understand is when I add two chemical reactions and when I'm going to get the third equation, you cannot directly add the reduction potential values. You cannot do that, right? Same way, I have A giving B, right? And say I multiply throughout, say for this it is E1, right? And say I multiply throughout the reaction by a factor of n, say I multiply throughout the reaction by a factor of 2 or 3 or 4, whatever it is, right? You can say I'll have Na giving Nb, you cannot write this as n into E1. No, you cannot do this. Okay, but still there will be a way by which I'll be able to find out this particular equation's is reduction potential value, right? There'll be a way by which I'll be able to do this. Okay, not directly in the form of reduction potential, but if I convert the reduction potential value, in terms of delta G, then I'll be able to do whatever I want, right? Say in this case, right, it is E1, and say now how will I write it in terms of delta G? Now can I say it is minus, so whatever the number of electrons, N1 F into E1, right? For this reaction I'll be, now this is the E1, right? If I convert this into delta G, it will be minus N1, whatever the number of electrons, I'll keep it as N1 F into E1, right? And for this reaction, say it is minus N2 F into E2, right? Now when I add these two reactions, I'll be getting this reaction. I can do this, I can even add the delta G values directly for the required equation, but you cannot directly add the reduction potential values. That is what I'm telling, right? So for this again, delta G, if I calculate, it will be minus of N1 plus N2 F into E, say this is E, right? For this reaction, N1 plus N2 is equal to F into E, right? and say for this the number of electrons actually lost or gained is N3. For this, the number of electrons gained or lost is N3 for this reaction. And again, this will be equal to the delta G of this equation, right? And this delta G is equal to delta G1 plus delta G2. That is, for this reaction, if I add the delta G values, I'll be getting the delta G of this equation, right? So that is how I got this. But for this equation again, I will have a separate delta G also. That will be equal to this. Say number of electrons lost is N3, some other number of electron, F into E. That is the value here. Sorry, this is not E, this is E1 plus E2. I'm sorry, this is N1 minus N1 E1 plus minus N2 F into E2. This is how I write the equation for this when I add these two equations, right? So obviously you will be able to take out F and F, right? So how will I find the E value here? E value would be equal to, again it's a minus sign, so minus also I'll be able to get cancel. So can I write it as E is equal to N1 E1 plus N2 E2 divided by N3. Correct? From this equation, from these two equations, I write E as N1 E1 plus N2 E2 divided by N3. That is how I write it. Correct? So this is how you will find the required reactions to reduction potential, not by directly adding them. First convert it to delta G, second equation convert it to delta G, and add these two or subtract these two equations to get the required equations to delta G. And that required equation will again have one more delta G with respect to number of electrons it lost or it gained, right? And equate them, and then you find the required reduction potential. Guys, understood? Please give me a yes. Guys,
Yes, sir.
everybody understood, right? Is it okay?
Yeah.
Right?
Yes.
Okay, now when we do problems, it will be more this thing for you. So we'll do a problem.
So can you give us time to copy this?
Yeah. Take it and take your time.
Yeah, none, sir.
Okay, good. So we'll do a problem. Right. So now they have given E naught Fe2 plus bar Fe is minus 0.439 volts and E naught Fe3 plus bar Fe is what is the equation? Minus 0.036 volts, and they're asking you for this reaction Fe3 plus accepting an electron to form Fe2 plus, what is the E naught value for this? Okay, they have given two equations, that is they are given two reduction potentials, that is one for Fe2 plus bar Fe, another for Fe3 plus bar Fe, right? And for this reaction Fe3 plus accepting electron to form Fe2 plus, what is the reduction potential for that? Okay, shall we do it? Right? Okay, fine. Now obviously you know how to write the reaction for this, right? For the first E naught, if I write the equation, can I write it like this? Fe2 plus accepts 2 electron to form Fe, right? And for this the reduction E value is minus 0.439 volts, and for the second reaction I can write it as Fe3 plus accepting 3 electrons to form Fe, and for this the reaction is what is it? Minus 0.036 volts. Okay, so fine. Obviously now what I can understand is, okay, now what I can understand is, see, first look at the equation here, right? I require Fe2 plus on the product side, correct? I require Fe2 plus on the product side, and I require Fe3 plus in the reactant side. Now go to the given equation. I have Fe3 plus in the reactant side. No problem. I want it in the reactant side, and it is there in the reactant side also in the given equation, right? But Fe2 plus is a problem. Fe2 plus in the required equation is in the product side, but here it is in the reactant side. So what will I do? Reverse it. Just reverse it, right? So when I reverse this, or how will I write the equation? I'll write it as Fe giving Fe2 plus 2 electrons. Correct? Fe, if I reverse the reaction, Fe giving Fe2 plus 2 electrons. Correct? Now, now you cannot add or subtract, or you cannot multiply. But whenever you reverse the reaction, you will be able to reverse the this thing, reduction potential value to the opposite side of that. So here it is positive. So here I can write it as negative. So it is be 0.439 plus 0.439 volts. This is the first step we'll do. Right? So look at where do I want certain things on the reactant side, look at where do I want certain things on the product side. Accordingly, if you want to reverse, you can reverse, or if everything is in the same place, you don't have to reverse anything. Right? Now you can understand, if I add these two reactions, Fe will get cancelled. Correct? 3 electrons, 2 electrons, 1 electron will be remaining. Right? And Fe3 plus will still be there, Fe2 plus will still be there. Yes, that is what I have to have. Correct? So basically, if I add these two reactions, I'll be getting this reaction. No problem. But I already told you that you cannot directly add the reduction potential values. You have to convert them into delta G. Then you have to add or subtract or whatever you want to do, you do. Right? Okay. First, if I calculate delta G1 for this, I can write it here. For this reaction, how will I write? It's equal to minus Fe. Right? How many electrons here? 3 electrons. So it is minus 3F into 0 delta G1 minus 3F into minus 0.036. Correct? For this reaction. Okay. And say for this delta G2, if I write, how many electrons here? 2 electrons minus 2F into what is the value? 0.439 volts. Okay. Now when I add these two reactions, I'll be getting this, right? So I'll be getting this. Say if I write before, like when I add these two, I'll be getting this, and for this I'll write the delta G first. Now delta G3 will be equal to, there is only 1 electron, right? Say it's 1F into the E naught value, which I don't know. Right? 1F into E naught value, which I don't know, right? And this value should be equal to sum of these two values, right? This value should be equal to sum of these two values. So I can write here minus F into E naught, that is this, is equal to sum of these two values. So I can write it as f. Okay, if I take minus f out, right, minus f into 3 into minus 0.039, that is this value, right, plus 2 into 0.439. Okay, so f and f gets cancelled. Okay, f and f gets cancelled, right? So this E naught value which I have is basically equal to okay, so now minus f got cancelled, like minus f and f both got cancelled, right? So what I have is 3 into 0.039 plus, oh, I already have a negative sign, so it's minus 3 into 0.039 plus 2 into 0.439, and that's the answer, right? Minus 3, but minus f got cancelled, so it is, I have 3 into minus 0.039 plus 2 into 0.439 is the answer. You guys understood? Please give me a yes.
Yes, sir.
Yes, sir.
So what about others? Everybody understood, guys?
Yes, sir.
Sir, at 0.036, sir.
0.036, sir. Okay, fine. Okay, fine. Hope everybody understood, right? So nothing, exactly what I told you in the previous general problem, the same thing I did here. Extra what I did is I reversed the reaction because I require Fe2+ on the product side. So I reversed it. I changed the sign of the E naught value. That's it, right? So I can calculate whatever the value is. So it will be 36, 72, 78, 108. So this value, if I write it at the top, now this value will be minus 0.108 plus 2 into this will become
0.878.
0.878, right? So 0.0878 plus 0 minus, so okay, so 0.878 minus 0.108,
0.770, sir.
that's the answer, right? 0.770 is the
Won't it be
answer.
negative, sir?
No, here I have, this is the negative value, this is the positive value. So obviously this is higher, right?
No, sir, in the left hand side we have written minus Fe naught, right?
Exactly, minus Fe naught and minus Fe naught got cancelled from this two.
So then we have a minus inside, sir. Like,
yeah, Kanna. So
Fe.
basically what I'm writing is I am oh, here also I have a negative sign. Correct. Cool. So here,
Sir, it's right.
correct only, right? Yeah, basically I took minus f outside. See, what you understand from this equation, if I add these two, I will take minus f outside from these two. So minus f I took outside, what is remaining? Minus 3 into 0.036. And if I take minus f out, what is remaining? 2 into 0.439 only is remaining, right? And then if I write the delta G3, it is minus f into E naught. So I cancelled minus f. So yeah, what I wrote is correct only, Kanna.
Okay, sir.
Okay.
I think so.
Cool. Yeah. So we'll do one more problem like this. Now you are going to do the problem. I'm going to give you this. If at all you need time, I can give you time. Please copy it soon. So hope you've taken it down. Okay, so here I have MnO4 minus plus 8H plus 5 electrons gives Mn2 plus 4H2O, and the E naught value for this is minus 1.51, okay, plus 5.51 volts, and I have MnO2 plus 4H plus 2 electrons gives Mn2 plus 2H2O. For this, the E naught value is 1.23 volts. So they want you to find for this reaction MnO4 minus plus 4H plus 2 electrons, sorry, 3 electrons gives MnO2 plus 2H2O. For this, find the E naught value. Okay, they are given two equations along with their E naught values. For this equation, find out. Go for it. Do the problem. Just 1 second, I'll be back. So what is the first step, guys? Do you have to reverse anything?
Reverse equation 2.
Correct. Correct. Because MnO2 in the required equation is in the product side, but here is it in the reactant side. So reverse it and change the sign of E naught. That is the first step.
That is the answer is minus 1.546.
Minus 1.54. I don't think so.
So plus 1.66.
Yeah, 1.66 should be correct, I guess. Plus 1.66 should be correct. Right, fine. So will I do this? Okay. So I already told you the first step is reversing. You're not able to see this. Okay. Fine. So the first step is reversing. So if I reverse this equation and write, it is going to become m into plus 2H2O gives MnO2 plus 4H plus it's 4H plus 2 electrons, and the E naught value will be minus 1.23 volts. No problem, minus 1.23. And for this reaction, I don't have to reverse, I can directly write it. So fine, I'll just do it and say I'll just write the E naught value alone. E naught value is plus 1.51 volts. Okay, fine. So for this reaction, that is this require, okay, I'll convert it to delta G. So for this, if I convert into delta G1 will be equal to how many electrons here? 2 electrons. So minus 2F into minus 1.23 minus 2F for this reaction, minus 2F into minus 1.23, so it will become 2F into 1.23. 2F into 1.23 minus becomes plus. Okay. Now for this reaction, if I calculate the delta G2, that will be how many electrons here for the first equation? 5 electrons. So it is minus 5F into 1.51, right? Minus 5F into 1.51 for the first equation, and this is for the second equation, which I have reversed. I have reversed the equation, and for this is the value. Okay, fine. For this equation, that is delta G3. Now delta G3 will become, what is it? How many electrons here? 3 electrons, so minus 3F into whatever the E naught value is, which I don't know. And this is again going to be the sum of these two reactions, that is the reverse reaction and this reaction. If I take the sum of it, I'll be getting this equation. So again, I'll be able to add the delta G values also accordingly. So this will be equal to delta G1 plus delta G2. So that will be equal to 2F into 1.23. This minus sign is still there. 2F into 1.23 minus 5F into 1.51 minus 5F into 1.51. Say I'll cancel the F's alone. I'll cancel the F's alone. So I have minus 3 E naught will be equal to 2 into 1.23 will become 2.46. 2.46 minus 5 into 1.51.
7.5.
How much?
7.55, sir.
7.55 minus 7.55, right? So if I write the E naught value, it will be, I think, minus 7.55 plus
0.09.
How much?
5.09.
5.09. Okay, and it's negative value, isn't it? So minus
Yes,
5.09 divided by minus 3. Minus 3 is there. So yeah, approximately you will be getting the value as 1.7 volts approximately. You'll be getting the answer as plus 1.7 volts. Okay, guys, understood? Everybody, is it okay?
Yes, sir, understood.
Yes, sir.
Okay, fine, done. So you want to have one more problem like this? Okay. Wait. whatever the type of problem which can be asked is asked. Okay. Fine. There is one more thing which you have to know in these kind of questions. Okay. Now see, in both the problems, what you did in the first problem as well as the second problem, in the required equation, say this is the required equation here. In the required equation, you saw some number of electrons coming, isn't it? In the required equation, you saw some number of electrons coming. Okay. Now, if you don't see any electron coming in the required equation, you don't see any number of electron coming in the required equation, you don't have to do any of this. You don't have to convert to delta G, then add again convert delta G into E naught. All this you don't have to do. You can directly add the E naught values. Please, you can even take it as a note. Write a note. Write a note. In the required equation, if there are no electrons, in the required equation, if there are no electrons, the E naught values of the given equations, can be directly added or subtracted. Right? So if there are no electrons in the required equation, right, the E naught values of the given equations, that's whatever is given in the question, the E naught values given, can be directly added or subtracted, right? But if there are electrons, you have to do it like this only. Convert them into delta G, then find the delta G of the third equation, then convert into E naught. That is what you have to do. But if it is a reaction where there are no electrons, you can directly add or subtract it. Okay, fine. So like this kind of questions can be asked. For example, say I have E naught Cr3 plus bar Cr, the value is given as minus 0.74 volts, and E naught Cd2 plus bar Cd cadmium is minus 0.4 volts. And say I have to find the Cr plus 2Cr plus 3Cd2 plus gives 2Cr3 plus 3Cd. What is the E naught value for this? Right? What is the E naught value for this? Now it's very simple. Okay. Right. Now let me look at the equations. Let me write the given equations first, and then we'll go for this. Okay. Say this. How will I be able to write Cr3 plus 3 electrons give Cr, and say the E naught value is given for this. I'll call it as E1 naught, E1. Okay. For this, Cd2 plus 2 electrons gives Cd. Okay. Now what you understand from this, see, look at here. I do not have any electrons in the picture, isn't it? In the required equation, I do not have any electrons in the picture. Correct. So what I should do? I can directly add or subtract the E naught values. So given E naught values, I can directly add or subtract. But before that, you have to make sure that the number of electrons lost and gained are equal. This is very, very similar to the previous cases. right? So now you have two half cells, right? So whenever you're going to get the overall cell reaction, what will you do? Before adding the reaction, before adding the cathode and anode reaction, you will make sure that the number of electrons lost and gained are same, so that the number of electrons getting cancelled. That is why you are able to subtract the E naught cathode minus E naught anode directly. Are you able to understand what I'm telling? Are you able to correlate what we are doing here and in case of your galvanic cells? Right? Just because there were no electrons in the overall equation in that case, that is your overall cell reaction, you were able to directly add or subtract the reduction potentials of the half cells, that is anode half cell and cathode half cell. You were able to directly subtract cathode minus anode, isn't it? Okay, fine. So now what I have to understand, do I have to reverse anything? That is the only thing which you have to understand. Now look at this. I require CD in the product side. Yes, CD in the product side. CD2 plus in the reactant side. Yes, CD2 plus in the reactant side. But when I go for the other one, I require Cr3 plus in the product side. But here it is in the reactant side. So first this has to be reversed. First this has to be reversed and wrote. So it is going to be this. I'll write it as Cr giving Cr3 plus 3 electrons. Cr3 plus 3 electrons. Now you have to make sure that the number of electrons lost and number of electrons gained is equal. Only then you will be able to get this equation. The required equation you'll be able to get only if I make sure that the number of electrons lost and gained are equal. So what I have to do? Can I say I have to multiply this by 3 and I have to multiply this by 2? You don't have to do anything to the E naught value. Just keep it. Say this is again for this it is E. For this it was E2, and now for this it will become minus E1 because I have reversed. This is for this reaction it is E1, and for this it will be minus E1. You know the values here also. Okay, fine. Now that's it. Now I'll be getting, when I add these two reactions, I'll be getting this reaction now. When I add this two, I'll be getting this reaction now. Now you can directly add these two. That is E2 minus E1 would have been the answer. That is basically minus 0.4 minus of minus 0.74 would have been the answer. Guys, understood? Everybody understood? Guys, is everybody okay with this?
Yes, sir.
Sir.
Right. So there are almost 15 students. I hear only 2-3 voices. Okay, we'll see.
Sir. Sir, the E1 value is minus 0.74, sir.
Correct. Yes. So now it will become plus 0.74.
Okay.
Okay. Right. So yeah, these are all the type of questions, and I can even ask you to find for this reaction, find the log of K. What is K? Equilibrium constant. Right. So I will be even able to ask what is the K value, log of K value, or even K value. Like why log of K? Because now you'll not be having the log books. That's why I'm asking you log of K. Now how will you find log of K for this? Very simple, right? Now what is you know an equation connecting my K value and my delta G. What is the equation? Delta G is equal to minus 2.303 RT log of K. Hope you remember this equation. Minus 2.303 RT log of K. This is the equation connecting delta G and K. Correct. Now delta G I'll be able to find for the overall equation because I know the reduction potential value. Correct. Delta G I'll be able to find for this reaction from the Z naught value. Basically this will be minus 0.4. That is E2. What is it? E2 minus E1. Right. So E2 is this. Minus of E1 will become plus 0.74. So when I do it, can I say it will be 0.3 volts? Right. Now this is the value for E naught for this acquired equation. Right. And I'll be able to find the delta G also. Right. Now when you're calculating delta G, now tell me what is the N value. Delta G is equal to minus NFE. That is okay. What is the N value for this reaction, guys?
6.
Sorry. 6. Yes, 6 is the value because now you have made sure that 3 into 2 will become 6, 2 into 3 will become 6. So the N value for this will be 6. F into E, whatever you calculated, and that is going to go to the delta G value, and then you will be able to find what is the K value. R value is 0.0821. R value should be No. R value should be 8.314. Now, please understand, guys, when and all you need to use R value as 0.0821 and when you have to use it as 8.314. So, whenever you are connecting my R value delta G or any type of energy, delta H, delta G, or any type of energy for that matter, now you know you're going to calculate the delta G value in terms of joules because that is the SI unit, right? And whenever you have joules coming into the picture, you have to use the R value as 8.314. So R value will be 8.314 if it is in terms of joules, right? And R value will be 0.0821 if everything is in terms of liter atmosphere or anything else, whatever comes. Right? Like if you're going to use it in the Nernst equation, at that time my R value will be 0.0821. But in this equation, that is whenever you're going to connect my delta G with my whenever you connect the R with anything with regard to energy, that is joules, right? At that time you have to use the R value as 8.314. You have to be very, very careful with these kind of problems. Okay, fine. So yeah, that is about connecting the thermodynamics with electrochemistry. Okay, so now I'll give introduction about the next part of this chapter. So yeah, one half is over. Your galvanic cell part is over. Okay, now we have to go to the not exactly electrochemical cell. Before that, there is one small part that we'll do. Then we'll move on. Okay. Right. So we are going to see something about conduction, right? Okay, fine. So we are going to start with something very, very familiar, which you have been studying from very, very lower classes, right? We are going to start with Ohm's law, right? Okay, so we already know what Ohm's law statement says, correct? So Ohm's law says that the current flowing across the conductor is directly, or the voltage difference or the potential difference across the conductor is directly proportional to the current flowing along the conductor at constant temperature, isn't it? You're talking about Ohm's law, and which we know what it already says. It says that the potential difference across the conductor is directly proportional to the current flowing through the conductor, right? So I already know V is directly proportional to I, and I know V is equal to I into R, where R is resistance, and we want to measure it in terms of ohms, right? All that we already know, right? Okay, now this is not from chemistry, but I'll ask you a logical question. Now we write V is equal to IR. Why can I not write I is equal to V and put a constant here? Why don't I write like this? Any idea, guys? I will not be writing the Ohm's law never as this. I directly proportional to I don't write. I always write V directly proportional to I. Why is it like this?
Because of only due to potential difference current
correct, exactly, right? So please understand, say I have two ends of a conductor. I have say point A and point B. Okay, so obviously say here it is V1, here it is V2. Only when I have this potential difference and to make the potential equal, the electrons will start to flow, or from this side to this side or this side to this side. And obviously only the electron flows, I say it as current, right? So please understand, only because that the potential difference exists, only because the potential difference exists, current is flowing. It is not the opposite. Just because current is flowing, I don't develop potential difference. Please understand that. Just because I have some potential difference and just because of the difference in potential between the 2 points, the current starts flowing. It is not the other way around. It is not like because of the current is flowing, I have a potential difference. No, it is not like that. That is why we always write V directly proportional to I and not the opposite. That is I directly proportional to V. Okay, anyways, so this is not important for us. Right. Okay. Now we already know what is this resistance. Like we know it is the opposition offered by the conductor to the flow of current. isn't it? Okay. Now you I hope you know this term. When I take the reciprocal of resistance, right? When I take the reciprocal of resistance, that particular value is what is called as my conductance. Right, the reciprocal, this is sigma. Sigma represents conductance, right? So reciprocal of resistance is what is my conductance. Okay, and hope you know already one more equation for R. I know R is equal to rho L by A, right? Rho is the resistivity or specific resistance, isn't okay? Before that, now you need to know what are the units for this conductance, right? Now I know the unit for R is ohms, right? Now for sigma, that is my conductance, it can be per ohm, ohm power minus 1, or even I can even write it like this, ohm power minus 1, or ohm power minus 1 can be written as mho, mho, right? Or I have one more unit called as S, Simon. S represents Simon. So all these units can be actually SI units, because all these represent same thing only. There is no conversion between these two. It's not like I have joules and calories. I have to convert. Joules is the SI unit, right? But for converting joules to calories, I have to do some multiply or divide by some factor. But here it's not like that. Per ohm, like this, mho, Simon, everything is same, right? So these are all the units. And in your electrochemistry, we'll be using Simon only. S will be the unit. Okay, so for your in electrochemistry we'll be using only Simon, not any other piece. Okay, S is the unit of conductance. Okay, so I already know R is equal to rho L by A, right? And I know this rho is what is called as my resistivity, and I know it is going to be ohm per meter, right? Ohm per meter is what is my what is that unit of resistivity, right? So again, if I take the 1 by rho, that is 1 by resistivity, right? Now that is going to be my K, that is my conductivity. Resistance, conductance, resistivity, conductivity, right? Reciprocal of resistance is conductance, reciprocal of resistivity is conductivity, and this K is a Greek letter. It comes from the Greek word kappa, KPPA. Nothing. K represents, K is the way of representation for conductivity. Okay, fine. Again, I need to know the unit for your K, which is going to be Simon per meter, or I can even write it as sometimes Simon per centimeter. That also can write, right? Simon per meter or Simon per centimeter will be the unit for conductivity. This is kappa, K. Okay, so please understand, 1 by resistance is sigma, that is conductance, and 1 by rho, that is 1 by resistivity, is my conductivity kappa, and the unit is Simon per centimeter or Simon per meter for this, and for conductance it is Simon. Okay, right? Fine. Now next thing what I have to know is, say if it is a solid conductor, if it's a solid thing, solid material I have, right? Now I'll be able to easily measure the resistance, isn't it? Right? I'll be able to easily measure the resistance, right? Now there I can directly measure the resistance value. Guys, do you know anything about something called as Wheatstone bridge? Have you heard of this?
Yes.
Sir.
Okay, so you would have studied about Wheatstone bridge, isn't it? So like I know why Wheatstone, like how Wheatstone bridge is used. So if I don't know any one of the resistance values, right? Now I'll be connecting in one of the arms of the Wheatstone bridge. I'll be connecting the unknown resistance, and I'll be able to calculate the resistance value very easily. Now if it is a solid, right? Now if it is a liquid, like an electrolyte, if I have an electrolyte which is composed of ions, right? I have two main problems in measuring the resistance or conductance or resistivity or conductivity. I have two main problems in measuring that, right? So what are the two problems I face? Right, the first problem is wires, isn't it? I will not be able to directly connect wires to the electrolyte. Like I said, it's a liquid, right? How will I say solder it or something? I will not be able to do this, right? So first problem I face is your wires. I will not be able to directly connect the wires to the electrolyte if it's a liquid. Solid I can connect, right? but for liquids and electrolytes, we will not be able to connect wires. Second problem is I will not be able to use DC. What is DC?
Direct current.
Correct. So I will not be able to use DC. Direct current cannot be used. Why direct current cannot be used? If it's a solid directly, I can have flow of current continuously, right? But if at all I have a liquid, if at all I have an electrolyte, direct current will alter the concentrations, right? Direct current will alter the concentration of the electrolyte. Obviously, the number of ions will change. Basically, the whole reason why that particular electrolyte is a conductor is basically because of the presence of ions, right? The charge carriers there are basically going to be ions, right? So if I supply direct current, the concentration of ions in the electrolyte will change, and thereby changing the resistance or conductance value also, right? So you cannot use DC. You cannot use DC. Fine. Now second problem can be easily overcome, right? I have only two main problems. One is I cannot directly connect wires to the electrolyte, right? Second thing is I cannot use DC. So the second problem can be easily overcome, right? How? Instead of DC, if I use AC, alternating current, right? Instead of DC, if I use AC, alternating current, then that problem is overcome. Okay, fine. Now, how am I going to overcome the first problem, right? How am I going to overcome the first problem? Now, there is a way for it, right? So the first problem can be overcome with the help of something called as conductivity cell, right? The first problem can be overcome with the help of something called as conductivity cell. Okay, so this conductivity cell is going to, like, fine, we'll see how the conductivity cell looks. Okay, say conductivity cell is going to be basically going to be a glass tube. Okay, so if at all you want to find any electrolyte, if at all you want to find any resistance of an electrolyte, unknown electrolyte you have, and you want to find the resistance of that, or say conductance of that, what you do is you fill this with the electrolyte first. You fill this with the electrolyte first. Okay, fine. Now I'm going to have two electrodes, that is this thing. What is that? Two electrodes placed in between. So the electrolyte is there filled here, right? So now I'm going to put the two electrodes into this, and that is the wires are connected. Now the problem of wires are gone. Correct. The problem of wires are gone now, because now I connected with the help of an electrode. Now I filled this glass tube conductivity cell with the help of the electrolyte, right? And there are two electrodes inserted, and I have connected wires. No problem, right? Now this will be taken to the Wheatstone bridge, right? This will be taken to the Wheatstone bridge, and I'll be able to easily find what is the resistance of this electrolyte, right? Say this resistance is Rx, right? If this resistance is Rx, I will be able to easily find what is the value of Rx by connecting it to the Wheatstone bridge. Now, how will I connect? Like, bear with my diagram, guys. Say this is my conductivity cell, right? This is my Rx. Now I have to use alternating current, not DC. This signal. Sorry, this is galvanometer. Sorry, this is galvanometer, and obviously this will be connected to the battery. Now remember, this is an alternating source, not direct current. Okay, fine. Now this is R1, this is R2, this is R3. Okay, so how do you remember Wheatstone bridge formula? Top by bottom is equal to top by bottom. Remember it like this. Top by bottom is equal to top by bottom, right? So top by bottom in the first case is R1 by R2, and in this case it will be Rx divided by R3, and you know every value other than Rx. Rx only you are going to measure, right? So Rx will be R1 by R2 into R3. So now I have found out what is the resistance of this electrolyte which is getting filled here. So again I repeat, there were two problems. The first problem was wire, second problem was DC. Now second problem can be overcome with the help of AC because the concentrations will not change, right? And first problem of wires can be overcome with the help of this particular thing called as conductivity cell. So this is how conductivity cell looks. It is going to be a glass tube in which I'm going to fill the electrolyte, and I'm going to fit 2 electrodes, and to those electrodes I connect with the help of the wires, and I take this conductivity cell here, put them in one of the arms of the Wheatstone bridge, right? And again, top by bottom, you will be able to find what is the resistance of this electrolyte. Okay, now there are still more things we'll be able to do in this, but I think we'll see it in the next class. Okay, so guys, any doubts till now? Is everything clear?
Yes, sir.
Okay,
Yes, sir.
fine, cool. So next class we'll be seeing how do you measure the conductivity. Now I know resistance, so I know the resistivity, right? But how will I measure the conductivity? For conductivity, I need to know the length. Say if I want to find resistivity, rho, if I have to know, I have to find the L value, A value, all these things I need to know, and I will not be able to directly measure it. Will I be able to measure the area easily, or will I be able to measure the length easily? This is not a linear thing which I'll be able to measure the length, right? So next class we'll be coming up with logical reasons or logical ways by which I'll be able to find the conductivity and resistivity and how you are going to do it, right? So until then, see, thank you, bye bye.
Thank you, sir.
Thank you, sir.
Thank you.